You know that feeling, right? You ship some code, you're sure it's perfect, and then boom, a bug crawls out of the woodwork. It's a programmer's worst nightmare. Well, today we are digging into a pretty radical idea that tries to solve this problem for good. Hoare logic. It's a system designed to prove, with actual mathematical certainty, that our code is flawless. I mean, really, how can we be 100% sure? We run tests, we debug for hours, we do code reviews, but does that guarantee anything? The famous saying goes that testing can only show the presence of bugs, never their absence. So to get to that level of absolute certainty, we're going to need a totally different kind of tool. So here's our roadmap. We'll kick things off with why this quest for perfect code is so important. Then we'll see how logic became the surprising answer. After that, we'll get into the real heart of it, Hoare triples, and the rules you use to build proofs. And finally, we'll tackle the biggest challenge of all, loops, and what it means for code to be totally correct.
All right, first up, this whole section is about a big mental shift. Moving away from just hunting for bugs and towards proving they can't even exist in the first place.
Just think about it. The code that's running a power grid, or a plane's autopilot, or even medical equipment in a hospital. In those situations, good enough is a recipe for disaster. We can't just cross our fingers and hope it works. We have to be able to prove it. So how in the world do you prove code? Well, the big breakthrough didn't come from better testing methods. It came from a completely different field, formal logic. And back in 1969, this was a mind-blowing idea. So Robert Floyd got the ball rolling in '67, but it was Sir Tony Hoare in 1969 who really just changed the game. He came up with this formal system, a set of logical rules that let you treat a program like it was a mathematical theorem. And suddenly, you could actually prove your program was correct, not just test it and hope for the best. Okay, let's get right to the absolute core of Hoare's system. The main building block for every single proof is this thing called a Hoare triple. It looks like this. You've got P, C, Q. It's really just a statement about your code. P is the precondition. That's what has to be true before your code runs. C is the command, the actual line of code. And Q is the postcondition. That's what's guaranteed to be true after the code runs. So basically it's saying if P is true when you start, then after you run C, Q will be true. Guaranteed. The best way to think about this is like a cooking recipe. The precondition, P, is having all your ingredients measured out and ready to go on the counter. The command, C, is you actually following the steps in the recipe. And the postcondition, Q, is that beautiful finished dish. See? If you start with the right ingredients and you follow the steps, you're guaranteed to get the right result. Now, Hoare didn't just give us this cool triple thing, he also gave us a whole set of rules, or axioms, to actually build proofs for all the different kinds of statements in a program. Let's take a look at a couple of the really important ones. So, first up is the assignment axiom. This is the rule for, the most basic thing you can do in programming, setting a variable's value, x equals e. Now, the formal rule for proving this looks kind of weird at first, but how it works is really the key to the whole system. And here is the absolutely brilliant trick. You don't reason forwards from what you have. You reason backwards from what you want. You start with your goal, the post condition, P. Then, to figure out what you needed at the very beginning, you just substitute the expression E for the variable x inside that post condition. And when you do that, it magically tells you the exact precondition you need. This slide shows you exactly why that backwards trick is so critical. Check out the correct example on the left. If our goal is to end with y equals 43 after running y equals x plus 1, what must have been true before? Well, simple. X plus 1 equals 43. It makes perfect sense. Now look at the total mess on the right if we try to reason forwards. If we start with x equals 5 and then run x equals 3, we end up claiming that 3 equals 5. It's just complete nonsense. So the takeaway is clear. For assignments, you absolutely have to work backward. Okay, great for one line of code, but what about a whole program? That's where the rule of composition comes in. And it's awesome. It works just like a chain of dominoes. If you can prove the first command gets you from state P to state Q, and then you prove the second command takes you from Q to R, then you've successfully proven the whole sequence takes you from P all the way to R. The postcondition of one step just becomes the precondition for the very next one. All right, now for the really, really tricky part of programming, loops. How can we possibly reason about a piece of code that might repeat a dozen times or a million times? And maybe more importantly, how do we prove it will ever stop? So this brings up a really important distinction. There's partial correctness, which is kind of like saying, hey, I've got a GPS route that will get you to the right place if you ever actually get there. It doesn't promise you won't get stuck in an infinite loop of traffic. Total correctness, on the other hand, is the gold standard. It proves both that your route is correct and that you're absolutely guaranteed to arrive. To prove a loop works, we need to find some core truth about it that just doesn't change. We call this a loop invariant. It's a logical condition that's true before the loop even starts. It stays true after every single pass. And because of that, it's still true when the loop finally finishes. Finding this invariant is like finding a stable anchor in the middle of a storm. It's the key to the whole proof. But to prove the loop actually stops, to get to total correctness, we need one more piece. It's called a loop variant. And you can think of this as a countdown timer. It's some value that we can prove gets strictly smaller with every single iteration of the loop. And, this is critical, it has a floor it can't go below, like 0. So since the value keeps dropping but it can't drop forever, the loop has to stop eventually. The countdown will always hit its end. What's really interesting is that Hoare himself, way back in his original 1969 paper, saw the practical challenges. He basically suggested that it's probably better to focus on proving conditional correctness, what we now call partial correctness, and just let the computer's implementation worry about runtime problems like running out of memory. It just shows this really pragmatic mindset from the very beginning.
And all of this brings us to the big final question. If these incredibly powerful logical tools have been around for more than 50 years, offering us a path to provably perfect code, then why is our digital world still so full of bugs? What's the gap between this beautiful, elegant theory and the messy, complicated reality of building software today? And that, well, that's the million-dollar question to leave you with.